Hello everyone. Imagine being able to process big data 100 times faster than traditional systems. Sounds incredible, right? Welcome to the world of Apache Spark. But what exactly makes Spark so lightning fast? Let's unravel the secrets behind Spark's powerful architecture. Spark architecture is a distributed computing framework designed for fast and efficient large-scale data processing, featuring a driver that orchestrates tasks across a cluster of nodes, where each node runs executors that perform computations across multiple cores. Spark follows a master-slave architecture. The master node, also known as the driver, is responsible for orchestrating the execution of tasks. It manages the cluster, maintains metadata, and distributes the work. The slave nodes, also called worker nodes, execute the actual tasks. Each worker node runs one or more executors, which are processes responsible for running individual tasks and managing data storage in memory or disk. Let's understand the Spark cycle. Upon the user submitting an application, the driver initiates a Spark session. The DAG, directed acyclic graph, creates a logical plan for all the operations, allowing Spark to optimize and schedule the execution effectively. The DAG scheduler in Spark divides the logical execution plan into jobs. A job in Spark is the highest level of computation and is triggered by an action such as count, collect, or save on a Spark RDD, data frame, or dataset. Jobs are broken down into multiple stages, where each stage consists of tasks that do not require data shuffling. A stage in Spark is a set of tasks that can be executed in parallel, determined by shuffle boundaries. A task is the smallest unit of work in Spark and represents a single operation on a partition of data. Tasks are executed by executors in parallel across the cluster, and each stage contains multiple tasks that process different data partitions. The task scheduler is responsible for assigning tasks to the executors on the worker nodes. When the code is ready for execution, the driver requests resources from the cluster manager for resource allocation. The cluster manager checks for available resources, allocates the required resources, and informs the driver. Upon confirmation from the cluster manager, the driver establishes direct communication with the nodes. The cluster manager monitors the nodes and manages node health, replacing failed nodes and adjusting the number of worker nodes as needed based on task complexity. The driver directly assigns tasks to the worker nodes and oversees task execution. The nodes execute the tasks using executors and return the results to the driver. A node can host multiple executors. The driver returns the results to the user or stores the output in a specified storage. Let's deep dive into a worker node. Consider a worker node configured with 4 executors, a 64-core processor, and 128 gigabytes of memory. Upon equal distribution of resources among the executors, each executor is allocated 16 cores and 32 gigabytes of RAM. Each core within an executor can operate independently, allowing an executor to handle up to 16 parallel tasks simultaneously. With its robust architecture, Spark provides a powerful, efficient platform for big data processing, making it a top choice for enterprises worldwide. Thanks for watching, and stay tuned for more insights into Spark.